Okay, fine. So, זה רק הפוינט. זה עובד אפילו. אוקיי, מצוין. All right. So, I specifically have in mind heat machines, or heat engines, if you like, and this is the subject around which thermodynamics has evolved, okay, for the past 200 years. So what are heat engines? All heat engines, ranging from power plants to single-atom devices, consist of the following ingredients. They are energized by a hot bath, so-called, which consists of a macroscopic number of degrees of freedom. Part of the heat is dumped into a cold bath, which also is macroscopic, and the difference is used by the working medium to produce work in a mode which is often called a piston, all right? So this means that all existing heat machines, and they have been so since Carnot for 200 years, are dissipative devices, and they perform two functionalities. One is that they concentrate the heat energy of these degrees of freedom to one, essentially, output mode, and the other is that they convert part of the heat into work. And the question is whether all these ingredients are essential for the functioning of heat machines, and we say no. In particular, and this is the take-home message, as Nadav advised me to show right away, that you can replace the conventional ingredients of heat machines by a nonlinear interferometer, which consists of a even small number of hot modes and of cold modes. And what is essential is that they are mixed by a nonlinear device. In most of what I'll say, I'll have in mind a cross-care coupler as a heat device. So what does it do? The cold modes, if they are transmitted through beam splitters with appropriate transmissivities, become weak copies or replicas of the hot modes. And then they are mixed by beam mergers, okay? And at this stage, you may say that the cold modes have measured the hot modes, okay? Although this is a linear and essentially coherent process, still they carry the information on the hot modes. However, if you want to make use of this information for operating a heat engine, this is not enough. And you usually resort to an observer, a Maxwell's demon, that reads out this information, the output of these measurements, as we have, for example, suggested last year, and uses this feed-forward to drive the machine in a certain way. And now we say that even that is not needed, provided you have nonlinearity. So what I'm trying to say is that this is an essential building block of a heat engine, and this block is completely coherent. It is a closed system consisting of a small number of degrees of freedom and has nothing to do with the conventional approach to thermodynamics, and yet it satisfies all the requirements. Now, before we came to this conclusion, we have gone through the motions of what is now called quantum thermodynamics, and all these papers are dedicated to that, our papers. And this is the conclusion to which we arrived. Basically, it is that there is not much in the attempt to add quantumness to machines that are essentially open systems, as all conventional heat machines are. Okay, so we demonstrated this with a very simple model, and that is a working medium which is just a two-level system that is coupled to a hot bath that has an average higher energy than the two-level transition, and to a cold bath which is resonant with it. Now, there is a surplus of energy here, and this surplus can be used by a piston, an oscillator mode, to amplify it and produce work. Now, this obviously obeys the laws of thermodynamics if you analyze this, and this means that the maximum efficiency you can get is bounded by 1 minus the cold bath temperature over the hot bath temperature. And it is even lower than that because the actual efficiency is the ratio of the output frequency to the input frequency. And the question is whether there is still any quantum advantage in such a device. In particular, is quantum coherence, as is often claimed, an advantage? And the answer is that not really, to say the least. So let us understand why coherence plays a role at all. Well, if you start off the piston in a state which is thermal, which means a distribution which is in the faceplate is centered at the origin and falls off monotonically, then the amplification will only produce heat. You will never get work out of this machine. To get work, you need to start it off with some coherence, which here means that the initial state is displaced from the origin. This is a so-called non-passive state as opposed to a thermal state, which is passive. And such a non-passive state can be amplified by the engine. As it is amplified, it produces work which is measured by the distance from the origin, okay? And it also gets heated. This is the yellow circle shown here. The distribution broadens, but this is a, a parasitic effect which can be relatively small. So the point is that as it evolves, the state of the piston becomes more and more classical, but it retains its coherence. In fact, as we know, coherent states can have infinite amplitude, yes, and then they become completely classical. Now, if you calculate the efficiency of such a device, you find out that the higher the amplitude of the piston, the higher the efficiency. And so being quantum is a clear disadvantage, as you see here. And only when you get to the classical limit, you can attain an efficiency which is comparable to Carnot. Okay, so it doesn't work here. Now, you may try to be more sophisticated, and instead of using a coherent state, you can use a squeeze state. We did that as well. And the result is that that too has a classical counterpart, so you cannot claim a unique quantum advantage there. Now, there was another proposal. Well, if it's not the piston that has to be quantum, then perhaps the bath. Okay, so people suggested a squeezed bath instead of a usual hot bath. And indeed, such a bath has higher energy than a usual thermal bath. And so they have attributed the surplus energy to higher temperature. And doing that, you arrive at the conclusion that the efficiency surpasses that of Carnot. That would mean, if this indeed is temperature, that the second law flies out of the window. Now, we looked at that and we came to a different conclusion. Indeed, you get higher efficiency than Carnot, okay? But it in no way violates the second law because the second law does not apply here, okay? Here is what you get. The efficiency, the Carnot bound is drawn here, and the efficiency surpasses Carnot as soon as squeezing in the bath becomes high enough, all right? And at the limit of very high squeezing, you reach unity efficiency. This is a false result by other people that predicted an efficiency higher than 1, which is, of course, impossible. But the point is that in this range where it surpasses Carnot, it is no longer a heat engine because what you get from the bath, a squeezed bath, is not just heat but also work. And so you have to modify the efficiency bound by 1 minus T cold over T hot times the ratio between the heat you get from the bath over the total energy, which includes a work component, okay? And this means that you commute work in the bath by work in the piston, and this is more a mechanical engine than a heat engine, okay? And the main point is that all of that has clear classical counterpart. So again, no quantum advantage. I could go on and on. We went through many such examples and got essentially disappointed by the possibility to produce something which would be spectacular and quantum in terms of the performance of a heat engine that is a conventional open system. So instead we have changed course and considered something completely different outside the usual paradigm, and that is a closed system consisting of only few modes. And this is the simplest example. It's a Mach-Zehnder interferometer, a two-mode interferometer. And what we add here is a nonlinear element. That's the cross-Kerr coupler. And the evolution here is tractable and fully unitary. You see, it's a product of linear transformation at the beam splitters and this cross-Kerr evolution, which is given by e to the I chi. Chi is the strength of the cross-Kerr coupling times the number of quanta in mode A and in mode B, okay? So what you get in such a device is that the phase of one mode is correlated to the intensity of the other. And as a result, the output that you get is non-thermal, okay? In each mode, you no longer have a thermal state. You have something which is even non-Gaussian and capable of producing work. Furthermore, you have here a control of the quantum statistics of the output, which strongly depends on the nonlinearity and on the temperature ratio of these two inputs, which again are thermal inputs. So you can see that the autocorrelation function can range from very large values, that's the so-called super thermal regime. 2 is thermal, and it can get much less than 1, i.e. be sub-Poissonian approach, a Fock state, if you like, as a result of this nonlinearity. So what's behind it? It is the preponderance of two-photon transfer from one mode to the other due to the Kerr cross-linearity. So here you see the photon statistics of one mode, which clearly has a higher probability for even photon numbers, quantum numbers, as compared to odd ones. And the opposite is true for the other mode. Okay, so you transfer pairs of photons mostly, and the photon statistics becomes then strongly non-monotonic, oscillatory. And if this is the case, then the state is a strongly non-passive state, and that means that it can deliver work. And indeed, you can plot the efficiency of work production by this simple two-mode device. The efficiency, i.e. the ratio of the work output to the heat input, and you see that you get sizable efficiencies approaching the, well, not really, but comparable to the Carnot limit, provided the G2 is strongly different than 1. Yes?
What fixes which mode will have odd or even?
Can I show it again? This is the mixing.
Yes, but
Yeah.
what fixes which mode will have odd correlation? The second one will
No,
have even?
both modes, each mode, this is, all here is plotted for separate modes. And each mode becomes non-thermal, non-Gaussian with quantum statistics, which is, you know, whatever you choose it to be.
Yes, but
by
you show us, for example, that n equal to 2, 4, etc.
Yeah,
in one of the
this
modes,
is
and in
okay.
the second mode is
Right, in the second mode,
what fixes the odd or even parity?
so why is it even parity?
No, how does the system decide in which mode to put the even
okay.
photon and the odd?
Fair enough. The colder mode, the one which gets the heat, gets even photon numbers, and the colder one then remains with the odd photon numbers. Yeah, okay. But this is still not a heat engine, not a bona fide heat engine, and for that you need a slightly more advanced version, which consists of 2 hot modes and 2 cold modes. But here you can really manipulate heat in the way which you can never do if this were a linear device. If it were a linear device, starting with 2 equal temperatures at the hot modes will always produce you equal temperatures at the output. You will gain nothing, no matter what you do. So you need to go non-Gaussian, and this is achieved again by cross-couplers. So again, as I mentioned in the first slide, the cold mode becomes the replica of this cold mode becomes the replica of this hot mode, and the same here. This cold mode becomes the replica of this hot mode, and then they mix at a 50-50 beam splitter, and what you get then inside the cross-care couplers is something which depends on the other hot mode. So the hot mode 1 is mixed with something which depends on hot mode 4 and vice versa. And so they become correlated. Not necessarily entangled, but definitely correlated. And what you get at the output is no longer something which you would have in a normal interference, because normal interference for thermal inputs would average out. You will have no interference effects, and as I said, the output intensities will be the same as the input intensity. But here, you can adjust the parameters such that most of the energy is steered to the mode you choose, and furthermore, they become non-thermal and capable of producing work. So this is, if you like, the basic building block of a heat engine, which is fully coherent, a closed system, and you can use it to create an even more complex machine, but I would say that this in itself is already a substitute for the usual thermodynamic paradigm of 2 heat baths coupled to a working medium. So you can, for example, cascade this 4-mode block as done here. The hottest output is fed into the next block. They are all identical, and each time you feed the hottest output, but these are non-thermal outputs, okay, because of the nonlinearity. And as you look at the photon number distribution, you see that progressively they become more and more non-passive, i.e. more and more displaced from the origin, which means they produce more work, approach the Carnot efficiency, and perform all the functionalities, the 2 functionalities of heat engines. Now, can we realize these devices in the quantum domain? And the answer is yes. One option is to couple a microwave cavity and a mechanical resonator by Josephson qubit. Such experiments have been done already, and the nonlinearity here is quite high. So this would be the analog of a cross-Kerr coupler for an electromagnetic and a mechanical mode, which means that you would be able, if you follow this design, to steer energy from mechanical modes to electromagnetic modes or vice versa. And the realization which we are pursuing at Weizmann with Ofer Fürstenberg is the following. We convert photons into polaritons. So this means that each photon becomes a collective excitation of cold Rydberg atoms, and then you make the polaritons, which counterpropagate in the medium, collide because they are coupled by a dipole-dipole interaction. Okay, and this is a strong interaction. The result is that they can already observe phase shifts of about pi caused by one photon when it encounters another photon, okay? So it's cross-Kerr effect at the level of single photons. And that's very promising. We are hoping to implement at least this Mach-Zehnder design using that. But still, we were looking for other realizations of the same idea, and we looked at spin networks, such as the one that Eugene Demler was talking about. So suppose we have a spin network which is coupled to two spin probes. Here there are these NVA and NVB. And the point I'm making is that in principle such a network could be the substitute for this cross-Kerr coupler because it has the essential nonlinearity that's guaranteed by the dipole-dipole interaction between spins. So you should be able, in principle, to transfer heat from one to another and concentrate their heat, as I was showing to you before. And of course, there are many other things. Yes? Many other things, before questions. Okay. There are many other things you could do with such a network, but there is a huge obstacle, and that is that this network has to be cold, i.e. essentially be at its ground state. If not, then it would be like a cross-Kerr interferometer with hot Kerr medium, and that's no good. Okay, that would disrupt coherence. And so one has then to cool down this network. And this is easier said than done because, and this has been a surprise when we first started looking at it, mostly it cannot be done. So let us now concentrate on such a network which you would like to polarize or cool down for a variety of reasons. This is what is called hyperpolarization in NMR. And you do that by a probe which swaps heat with this network and dumps this heat elsewhere, okay? But this doesn't work. And the reason is that symmetry plays a crucial role here. You can see here what happens when you perform, no matter what operations, swapping heat between the network and the probe and then dumping the heat away. Only among these three configurations of three spins in the network, only this one can be fully polarized. You can see it here. Only this one reaches full polarization. The others are stuck at somewhere near 0.6 polarization, okay? And when you go on to more complex configurations, you see that it is very hard to understand why some are polarized and some are not. So among these four spin configurations, only this and this are polarizable. The others are not. Well, the solution to this riddle is that it is all determined by the topology of the network, okay? So if you try really to calculate the ability to polarize a network, you run into the problem that I mentioned the other day, that if you have, say, 7 spins in the network, and you try to look at what consecutive operations do to it, it takes 1 month for each such run, okay? That's for 7 spins. For 10 spins, it's utterly impossible, even if you decide to spend years, okay? What is the requirement that you have to satisfy? You have to satisfy the requirement that the rank, the number of independent solutions of this map that you apply to your network must be equal to, to its dimensionality. If it's not, then the network is not polarizable. And here, what we have found is that we are saved by graph theory. Because if you classify the graphs according to their symmetry under permutation, then you see that permutable nodes have the same color, okay, that's how you choose to do that, and only if you have no degeneracy, no multiplicity of these permutable nodes, you can polarize the network. And the reason is that whenever you have multiplicity, you have inevitably dark state lurking there, okay? So this cannot be polarized unless there is absolutely no degeneracy, no multiplicity. So this saves the trouble of diagonalizing the matrix, and you can, just by observing the graphs, you can determine the degree of polarizability of the network, and we find this quite promising. So here are the conclusions. I started with the thermodynamic paradigm in which heat machines are open dissipative systems, and have looked for quantum advantage in heat machines, but at least the main mechanism that we looked at have classical counterparts. So then we turn to a paradigm change in which heat machines are replaced by closed non-dissipative coherent systems. And the simplest one are two-mode correlators, such as a Mach-Zehnder interferometer with Kern nonlinearity. Okay? Then if you go to 4 modes, you get the full equivalent of a heat machine. And if you want to implement the same in spin networks, you should be mindful of their symmetry, their topology, and in some cases you can do that, and in others you are stuck because of the presence of dark states that prevent thermalization. Thank you very much.
Thank you. This talk is open for questions. Wow.
So regarding your implementation with beam splitters and Kern nonlinearity, can you operate in the refrigerator regime?
Yes,
and if yes, what would be the
yes,
power? What would be the power?
But it is a bit more complex.
What would be the power that you put in? What would be the power that you put into the system in order to cool?
Yeah, you need well, it could be again thermal input, but it has to be high enough so that it provides the energy for the refrigeration. But it's not the same design as the one.
It would be like an absorption of the
Another system that comes to mind, like the way you define it, is Fermi mixtures in cold atoms, because you can naturally prepare different hyperfine states with different temperatures. Contact interaction is your mixer. RF rotations is exactly your beam splitters. So you can do all kinds of simulation, but the question is how would you define work? Like just because how the cloud expands, or?
Okay, well, so we have the formal definition, if you like, and it's here. You see, work is the difference between the mean energy of your output, okay, and the passive energy. And the passive energy is the energy which is associated with the monotonic distribution. So if you have here a non-monotonic distribution, you have to deduct the monotonic distribution, and what remains can be converted into work. So this is a strict definition of work, and I'm sure you can apply it to cold atoms, but of course it takes some consideration. In any distribution, you have a monotonic form, monotonic fall-off of the distribution, and that is not work, that is essentially heat. So you have to deduct that from the mean energy, and what remains is work.
Okay, thank you very much. Another question? Please. A quick one.
So you emphasize that previous attempts in the literature have classical counterparts, so they're not entirely quantum. And then you mentioned that the four-mode coherent heat engine is not necessarily entangling. So what is the quantum signature? Is it the sub-Poissonian statistics, and how do you use it?
It's sub-Poissonian statistics, but that's not a signature of entanglement. Yeah. But these two modes don't satisfy the criteria of entanglement, the output modes. You start with thermal, but when the input is no longer thermal, for example, you go for multiple iterations, then you can go non-classical as well.
Oh, okay, thank you.
Okay, so in the interest of time, thank you, Gershon.
Yeah,